Hi, and thanks for joining me in this video on pressure sensors. We're working our way through mercury barometers right now. And there are many different types of mercury barometers. There's the siphon, the weight, and the cistern. The siphon and weight are not very common, but the cistern was been around for a long time, and it was a standard actually with the National Weather Service. So let's take a look at these barometers. First, the siphon barometer is one. Of course, it's a mercury barometer. It's constructed so that the upper and lower surfaces have the same diameter, sometimes in the form of a manometer with the tube being open and, of course, filled with mercury. This is not a very common meteorological instrument, but you do find it back in historical instrumentation. Likewise, a weight barometer is also one that you don't find very often. It's not typical, but it's one where of course, it's a barometer filled with mercury, and as atmospheric pressure changes, the weight of the mercury in the column changes. You can weigh the cistern and from that get a measure of the pressure. Don't see these very often. The ones that are more common, as I mentioned, these are standards, is the Cistern Barometer. And the cistern is one in which the lower mercury surface is larger than the upper mercury surface. And they can be classified as either Q or Fortin. The Fortin barometer has been used quite frequently at the National Weather Service. So the Cuberometer is one where you can't adjust the cistern. In other words, you can't move the mercury up or down. There's no adjustment for the variation of the level of mercury in the cistern as pressure changes. So they work it such that there's a contracting scale that's used to measure the height of the mercury column. The one that's more common, and it was a standard with the National Weather Service for years, was the Fortin barometer. And this is one, it's a cistern barometer, so it has a lower bowl of mercury that's adjustable. The cistern is adjustable. The pictures that you're seeing here are pictures of our cistern barometer. When I first started teaching this class in 2006, we had two Fortin barometers mounted in our instrumentation lab. They have since been removed because mercury is toxic. This is a cross-section of a Fortin barometer, specifically the lower cistern, and it shows the tube going up, the barometer tube, and then a lower bowl, which is called the cistern, which is filled with mercury. Typically, this bowl, the exterior is actually made of leather, and there is an adjusting screw at the bottom that you can screw up and down so that the cistern level will rise or fall. And likewise, the mercury in the barometer tube will also rise and fall. And then there is a fiduciary point where you're supposed to screw up the mercury so it's just touching that fiduciary point. And at that time, you can make an accurate measurement of pressure. Speaking of measurement of pressure, that's done using a Vernier scale. And what it was devised by Pierre Vernier back in 1766. And it's a scale that slides along the instrument, along the barometer tube at the very top. And it's, I should say, the resolution is increased when you use a Vernier scale. This is what it looks like on our mercury barometer, one that we got rid of years ago. But the idea is to put as you can see in the picture at the bottom, there is a sliding scale that goes up and down the front of the tube, and you are supposed to move it so that the metal, the top of the metal, meets the meniscus of the mercury, in other words, the mercury column. And then you can match up, you can first get an estimate of the height using kind of a rough estimate. And then after that, you look for where the scale meets up, and from that you can determine the height of the mercury column to the nearest tenth of a millimeter. And this is just a little bit close-up of showing you two different Vernier scales, one with 10 divisions, the other one with 20 divisions, but showing you how when you look for or you estimate first at the zero, you can see on the left side it looks like it's approximately 912, 911, 912. In this case, I think it's millibars. And then as you look up the scale where it matches, that gives you a little bit more precision. And you can see that the scale matches up near the eighth, so that would be 8/10. So that's how you can read or how you can use a Vernier scale. Not many people use these anymore, of course. Calibration for mercury barometers. We use the same calibration equation that we did for the manometer. Pressure is equal to the height of the mercury times the density of the mercury times gravity. And the problems, though, we assumed before in our discussion that mercury was, of course, the density was constant, and the same thing with gravity. We assume that gravity is pretty much constant. Well, actually they vary. And we have to account for that. But in looking at the sensitivity of a mercury barometer, sensitivity is how much the mercury column will change for a given change in pressure. And it's the same equation as we had for the manometer. And we did some calculations in a previous video to figure out the sensitivity for both a mercury and also a water barometer. So here's some of the errors and some of the corrections that are made for a mercury barometer. Number one, there is temperature errors, so there's a correction for that. The density of mercury, just like any fluid, varies with temperature. And also other parts of the barometer also expand and contract with different temperatures, the glass and also the metal. So there needs to be a temperature correction that needs to be made to your measurement to get a correct reading in the height of mercury. Not only that, but also there is a gravity correction. You know that gravity varies with latitude. As you move north or south, you get different values of gravity. And also, as you move up through the atmosphere, you know that gravity decreases. So you have to account for not only latitude, but also height. There are other errors we talked about. There may be a little bit of mercury vapor at the very top of the barometer where there should be a vacuum. That's caused by the evaporation of mercury, but we said that mercury doesn't really evaporate very much, so that might cause a very small error. Also, making any measurement of pressure, if your barometer is inside and there's strong winds, then the building has a slight lower pressure caused by the wind blowing around and over the building. It causes actually a little bit of a vacuum inside the building, so your pressure measurements will be a little bit lower. And then finally also trying to interpolate the height of the meniscus or the height of the mercury column sometimes can be a little bit of a problem because of the clinging of the mercury to the sides. It doesn't cling as badly as water, but still there is a little bit, so it produces a depression in the mercury, and that causes errors also. And then finally, there may be impurities in the mercury, meaning that over a period of time it collects other elements besides just mercury. And as a result, of course, the density will vary. It's nice to have very clean mercury. Typically, when you get a mercury barometer, first get it, the mercury is bright, and if it's contaminated, then it shows up as a dull gray. So here are some of the corrections that can be made to a mercury barometer. These are corrections to get the correct station pressure. Now remember, station pressure is the pressure that's measured at a given height. Of course, that varies, of course, with the elevation. And the corrections that need to be made are, of course, temperature corrections. Also, if their instrument has some systematic errors, you have to correct for that. And then finally, the last correction that needs to be made is for gravity. So here are how the corrections are made. First, you have to do a correction for instrument error and temperature error, and then finally gravity to get the station pressure. A little bit more detail. First thing you do is correct the pressure. You take the pressure and then you correct it for index error. And this is done by comparing your barometer with a standard barometer to find out what the errors in your barometer are. If you don't know what your index error is, then you assume 0. The next correction that is made is for temperature, and this is caused by the expansion and contraction of Mercury and also of the scale. So we have expansion coefficients for Mercury and expansion coefficients for the scale, and that's a function of temperature. Multiply that by temperature and then multiply that again by the pressure that you measured, and that'll give you a correction that you need to make to the pressure. So your index error, add that plus your temperature error, your correction, to the pressure that you measured, and that will give you your corrected pressure. Now finally, take that corrected pressure and then modify it for a correction based on gravity. Your local gravity depends upon the latitude and also the height of the station above sea level. Of course, gravity varies because the Earth is an ellipsoid. At the poles, the gravity is more than it is at the equator. At about 45 degrees latitude, we assume that gravity is about 9.8 meters per second squared, and we call that standard gravity. So the first correction that we make is at sea level, we correct for latitude, correct gravity for latitude. Here's the equation, and it is pretty complicated and it's easy to make errors. After you get the corrected gravity for your particular latitude, then you need to make the correction for height. And not only do you need to figure out your height in meters, but also the mean elevation in the surroundings, and subtract the two, and then make that correction to your gravity at your latitude to get gravity at your location. Then here's the final correction. Take the standard gravity, also the gravity at your latitude for a given altitude, multiply it by pressure, and that gives you the pressure that you corrected for index and also for temperature. And that gives you the correction that you need to make to pressure. Finally, add that correction for pressure for your gravity to the previous correction, or previous pressure that you corrected, to finally get station pressure. So that gives you a quick overview on all the errors that are associated with mercury barometers.